Hi everybody, welcome back. So in today's session, we are going to learn to calculate crystal field stabilization energy. Please pay attention to each and every word. Crystal field stabilization energy, and that is what is written as CFSC. Crystal field stabilization energy. Understand that crystal field stabilization energy is not equal to crystal field splitting energy. Okay, so in CFSC, the S stands for stabilization, while this delta O, delta T, or generally delta, that represents splitting, crystal field splitting energy. So please pay attention to this. I have seen many students who keep on switching on between crystal field stabilization energy and splitting energy. For both of these, they just write CFSC. No. CFSC, S stands for stabilization energy and delta is for splitting energy. Okay, so in today's session, we are going to discuss to find the crystal field stabilization energy for which you should know the splitting. Okay, so we have already, I know that I have given certain questions in the previous session. I'll be taking up that question. Before that, let me just tell you how to calculate CFSC so that we can apply the same formula for all the complexes which were given. Okay, so so understand that CFSC is for stabilization. Okay, so crystal field stabilization energy is very simply the energy released. It is the amount of energy released, okay, due to the splitting of d orbitals. Okay, so this is the amount of energy released as a result of splitting. Okay, let's say that you have two species. One has got a CFSC of minus 0.4 delta O, and the other one, let's say, has got a CFSC of minus 1.2 delta O. Which one is stable? Understand that minus notates stabilization. Okay, so on the left hand side, the system is stabilized by only 0.4 units, while on the right hand side, it is stabilized by 1.2 units. Okay, so you have to take the modulus. If it is negative, negative indicates it is stabilized. Now, which is more stabilized? This one. This one is more stabilized. Are you getting my point? Let's say you have a complex where CFSE is plus 0.4 delta O, and over here CFSE is plus 1.2 delta O. In this case, understand that minus, okay, let me not confuse you. Minus stands for stabilization. Okay, here you have plus. Plus stands for destabilization. Note it down if it is confusing. So here it is destabilized by 0.4. Here it is destabilized by 1.2. So this is more stable. Understand the concept and do not take the scale and you see that minus 1.2 is over here, minus 0.4 is here, 0.4 is here, 1.2 is here. No, this approach is wrong. You have to understand it on the basis of the amount of energy released. So if it is negative, it means stabilization. If it is positive, it means destabilization. Okay, that's it. That's how you do it. Now, if you have any system of DN configuration, let's say it is octahedral or tetrahedral, whatever it is. Let's say we are considering for octahedral species. So for DN, okay, so we'll consider both octahedral and tetrahedral species. So DN, in octahedral case, your DN electron would be first distributed in T2 Okay, and depending on the splitting, it might go to Eg, it might not go to Eg. So the total number of n electrons would be distributed as T2Gp and EgQ. You will understand it when we do problems, don't worry. Okay. Now, the crystal field stabilization energy is equal to number of electrons that have entered T2G is P into each of these electrons would have an energy of minus 0.4 delta O plus number of electrons that have entered Eg is Q and each of that will have an energy of plus 0.6 delta. This is how you find CFSE of an octahedral complex. Okay. If it is tetrahedral, very easy, just reverse it. If it is Dn, first it will enter into E, where let's say the number of electrons are P, and then it will enter T2, where it is Q. So in tetrahedral geometry, the crystal field stabilization energy is equal to P times E is at the bottoms, stabilized by minus 0.6 delta T plus T2 has got Q electrons plus 0.4 delta T. This is how you find crystal field stabilization energy. Okay. So corresponding to all the complexes that we wrote in the previous session, we are going to try out the configuration and we'll also try out to calculate the CFSE. Let's do it. Okay, I hope it is clear. You'll understand it better when we do the problems. So let's start. Cobalt NH3 6 times 2 plus. Ammonia NH3 is a neutral ligand. So cobalt over here is plus 2 in oxidation state. Correct? Ammonia is a weak field ligand with respect to cobalt 2 plus. You have to be careful of cobalt 3 plus. Okay, this is cobalt 2 plus, so you're on the safe side. And the configuration is D7. Correct? So how do you fill it? You have T2G and you have Eg. You have to fill 7 electrons and the ligand is weak. So 1, 2, 3. The fourth electron will easily jump to the Eg orbital because it is weak, and then 5, 6, 7. This is how you see the configuration. Okay, so that corresponds to T2G5EG2. Now, how do you calculate the CFSE of this? 5 electrons in T2G, meaning 5 into minus 0.4 delta O, plus 2 electrons in EG, 2 into 0.6 delta O. So this is minus 2 plus 1.2. And that gives minus 0.8 delta O is the crystal field stabilization energy. Crystal field, please pay attention to my words. Crystal field stabilization energy is equal to minus 0.8 times crystal field splitting energy. So this is negative, meaning it is stabilized. Energy is reduced. Energy and stability inversely proportional. Okay. So if energy is less than 0, stability is high. So it is stabilizing. Got it. Okay, next. Cobalt 3 plus, as water is neutral. Generally, water is a weak field ligand. But over here, you have cobalt 3 plus, which shows exceptional nature. Only a few ligands will act as a weak field ligand with cobalt plus 3. Right? Those are fluoride, chloride, bromide, iodide, azide, and SCN minus. Except those, everybody is strong. So over here, this water will act as a strong ligand. Will act as a strong field ligand. It's not a strong field ligand, but because cobalt 3 plus shows exceptional behavior, it will act as a strong field ligand. Cobalt 3 plus is D6 in configuration, right? So you have T2GEG. You have T2GEG. You have to fill 6 electrons, 1, 2, 3. But the fourth electron won't jump because This is a strong field ligand. The gap will be very huge. The fourth electron cannot jump and hence it will pair up over here. I don't have space, that's why I'm not showing it. But then understand that the splitting is very huge because it acts like a strong field ligand. So the configuration is just T2G6EG0. Okay, what is the stabilization? Minus 0.4 delta O into 6, which means minus 2.4 delta O. Crystal field stabilization energy is minus 2.4 units of crystal field splitting energy. Next, be careful. Cobalt 3 plus again. Cobalt 3 plus, any ligands, majorly, most of the ligands would act as a strong field ligand except a few. Cobalt 3 plus is D6. This is something that we have just done now. So the splitting will be huge. As a result, 1, 2, 3, the fourth electron cannot jump, will pair up at the bottom, and your configuration would be T2G6EG0. CFSE is 6 times minus 0.4 minus 2.4 delta O. Okay, good. Next, cobalt is plus 3 over here. Fluoride. Fluoride along with cobalt plus 3 will act as a weak field ligand. And here the configuration is D6. So now you have T2G and EG with a very small gap because it is weak field ligand. 1, 2, 3, fourth electron can easily jump because it is a weak field ligand. Splitting would be low. And then 6 pairs up at the bottom. So T2G6, EG2. Okay, so how much? Minus 0.4 into 4 is minus 1.6 delta O. Plus at the top you have 1.2 delta O, which is minus 0.4 delta O. This is the crystal field stabilization energy. I'm repeating it again and again so that you understand. Okay, so among cobalt 3 plus, if you look all the question papers, these are the only two complexes where you can see that they behave like a weak field ligand. Rest, whatever ligands are given to you, they'll act as a strong field ligand, which was asked in the question paper. But the list of the ligands which are actually weak was given by me in the previous session. But just note these two complexes. Okay, this is just as expected. Fluoride is weak. This one would also be weak. So again, cobalt is in plus 3. So you have 1, 2, 3 easily. 4 can jump because the splitting would be low and 6 would come over here. T2G4, EG2. Okay, it's not 6 over here, it's 4. It's my mistake. It's T2G4, EG2. Here also T2G4, EG2. So again, the CFSE is going to be the same, minus 0.4 delta O. Okay. All right. So these two complexes are the only two complexes of cobalt 3 plus which has been asked in the exam where the ligands act like weak field ligand. Remaining all the complexes which were asked in the question paper, that is ammonia. See, this was asked already in the question. All whatever we are doing are all PYQs. Okay, you can see that it is acting as a strong field ligand. Water, strong field ligand. So whatever you use, they would be strong except these two complexes. So you should know these two complexes. Okay, next question. Rhodium. Oxidation state of rhodium is plus 3. It's cobalt, rhodium, iridium. We said that if you have metals where they belong to 4D or 5D, whatever the ligands are, they would act as a strong field ligand. Correct, because the overlap is so high that the splitting would be high. As a result, T2G, EG gap would be huge. It's just like cobalt 3 plus D6 configuration. So you have to fill 1, 2, 3. Splitting is huge. 4, 5, 6 will pair over here itself. T2G6EG0 is the configuration. And the CFSE is minus 0.4 into 6 delta O, which is minus 2.4 delta O. All right. Next one, water is neutral. Chromium would be 3 plus. Scandium, titanium, vanadium, chromium. Okay, so chromium is actually 4s2 3d4. Scandium, titanium, vanadium, chromium. Actually, this is 4s2 3d4. So here it is 3 plus. So 2 electrons will go from S and then 1 will go from D. So meaning it will be D3. And this is a 3D metal. If it is a 3D metal, you have to check whether it is a weak field or a strong field ligand. Water is a weak field ligand. So if water is a weak field ligand, T2GEG gap will be small. As a result, 1, 2, 3, only these many electrons, easy. T2GEG, T2G3EG0 is the configuration, and crystal field stabilization energy is equal to minus 0.4 into 3, which is minus 1.2 delta O. All right. Next question. Iron oxidation state +2. Iron in oxidation state +2 is D6. It's a 3D metal. You have to check whether it is strong or weak. Cyanide is a strong field ligand, meaning the splitting would be huge. If the splitting is huge, you have to fill 6 electrons. 1, 2, 3. Fourth one cannot jump. 4, 5, 6 will pair over here. T2G6EG0 is the configuration, and CFSE would be minus 4 times 6 into delta O, which is minus 2.4 delta O. Okay, next one, nickel. Nickel is in +2 oxidation state, D8 configuration. D8 is a special configuration which we have said earlier from valence bond theory. We said that if the coordination number is 4, D8 along with the weak field ligand gives you tetrahedral geometry. Correct? D8 with a weak field ligand, chloride is a weak field ligand, will give you tetrahedral geometry. So in that case, E would come at the bottom, T2 will come at the top. Okay? So it's a weak field ligand. Even if it is a weak field ligand, understand that in tetrahedral complexes, you can note it down if you want. Note, tetrahedral complexes always form high spin complexes. That means the gap would be small. The gap would be small. So here you have 1, 2. You have to fill 8 electrons, right? So 3 would come over here, 4, 5, 6, 7, 8. 2 unpaired electrons total. The configuration is E4, T24. What is the value of CFSE? So you have 4 electrons in E, which is stabilized, minus 0.6 delta T into 4, plus 0.4 delta T into 4. Correct? So this gives you 4 into 6 is minus 2.4. And at the bottom, what you have is plus 1.6, which means minus 0.8 delta T. Minus 0.8 delta T. Okay. Last one, iron is in -2 oxidation state, which means iron is in, yeah, -2 oxidation. Let me check the question. Yeah. Iron is in -2 oxidation state. So iron is actually 4s2 3d6. This is iron. But then it has got 2 more electrons and hence it will become 3d8. S2d8. We have said that whenever you have S2d8 with 4 ligands, it is an example of converted D10 system. Converted D10 system. Converted D10 system Actually, carbonyl is a strong field again, but that is of no use because it is tetrahedral over here. E at the bottom, T2 at the top. Tetrahedral complexes always form high spin complexes. As a result, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the configuration is E4, T26, total CFSE if you calculate, it would be equal to 0. Okay, so this is how you actually find the crystal field stabilization energy. Okay, now in certain questions, they will also ask you about the pairing energy. Pairing energy. So let us discuss that as well. So you write crystal field stabilization energy and pairing energy. Again, this is important. Now, this is actually, okay, let's do it from D1, D2, D3. Let's say you have D1. So we are talking about octahedral complexes, let's say. So you have T2G at the bottom, EG at the top. So let me please write it over here. Okay. So if you have just one electron, the configuration is T2G1, EG0. And the total CFSE over here is just one electron corresponding to T2G minus 0.4 delta O. Right. No pairing of electrons. Easy. All right. Next, let's say you have D2. So in D2 also, you have just two electrons occupying in T2G. As a result, the configuration is T2G2EG0. And the CFSE over here is 2 into minus 0.4 minus 0.8 delta. Right. No pairing. D3 system, you have 3 electrons, 1, 2, and 3. So it is T2G3EG0. No pairing. CFSE is minus 1.2 delta O. Okay. Now, when it comes to D4, understand, D4 can have two states. It can be of two possible states. One is where 1, 2, 3, fourth one goes to the top. This is a high spin complex. This is a high spin complex. And the other case is where you have 1, 2, 3, and instead of jumping to the top, it just gets paired over here. And this is a low spin complex. Okay. So what are the CFSEs? So over here, the CFSE is equal to, you have 3 at the bottom, minus 1.2 delta O, plus 2 in EG, corresponding to plus 0.6 delta O. That is equal to minus 0.6 delta O. No pairing. No pairing. But in D4, pay attention. In D4, you have CFSE which is equal to minus 0.4 into 4, which is 1.6 delta O plus 1 pairing energy. See, it requires a minimum amount of energy for the electrons to get paired. Because electrons are occupying the same orbital, electron-electron repulsions would happen. And as a result, you need to give some amount of energy so that these two electrons can occupy the same orbitals. Okay, why is it getting paired? Important. Why is it getting paired over here? Because the pairing energy is less than that of the crystal field splitting energy. The pairing energy might be just 100 units, while the crystal field splitting energy might be 1000 units. So it was easier for the system to get paired instead of jumping up. While over here, the delta O was less in compared to that of the pairing energy. Here, if the splitting energy was, let's say, 100, the pairing energy would have been 1000. So instead of pairing, it would opt for jumping to EG. So here there is one set of paired electrons corresponding to which you have to add one pairing energy, and that is the CFSE. Okay, let's try the next one, D5. That will also come very easily to you. D5, let's say high spin. High spin means 1, 2, 3. Easily, the fourth one can jump. Fifth one will also occupy EG. So the configuration is T2G3EG2. And the CFSE, if you calculate, this is equal to 0. Okay. None of them are paired. So no pairing energy. Over here, 1, 2, 3. It cannot jump because it is a low spin complex. The splitting energy is large. So instead it will get paired over here. Here the configuration is T2G5EG0 and the CFSE is going to be minus 2 delta O plus, important, that's not it, plus 2 of the electron pairs are paired plus 2p because 2 of them are paired. Okay. This is also easy. Next one might be confusing. Mark that as important, and that is what was asked in the question paper. D6. So when we have D6, there are two possibilities. One is 1, 2, 3 jumps and then pairing occurs. Okay. So here the configuration is T2G4EG2. CFSE is equal to 4 into minus 0.4 delta O plus 2 into plus 0.6 delta O, which is equal to minus 0.4 delta O. This is CFSE. Understand that there is no pairing energy added over here. It's not plus 1p. No. There won't be 1p. Even though you can see one pair of even though you can see one pair of electrons which are paired, you need not add one pairing energy because this is just natural. You're not giving any energy. Every one of them is half filled and then pairing occurs. And that is natural. You need not give any energy. Okay, that's the Hund's rule of maximum multiplicity followed by Pauli's exclusion principle. In the earlier case, that was not the scenario. Here, instead of singly occupying, it is first get pairing for which you have to give some energy. That's why you have to add pairing energy. Here, every one of them is singly occupied and then only pairing is happening, and that happens naturally, for which you need not add pairing energy. Important. Okay. Let's say you take a low spin complex. So you have 1, 2, 3, 4, 5, 6. The configuration is T2G6 and the CFSE value over here is 6 into 4 minus 0.4. It's minus 2.4 delta O. Important, it's not plus 3 pairing energy. You might see 3 sets of paired electrons, but it is not 3 pairing energy. Instead, it is just 2 pairing energy. CFSE is just 2 pairing energy. Why? Why? Because, see, naturally what happens is if there were 6 electrons, understand, if there were 6 electrons, very naturally one among them would get paired. Do you understand my words? If you did not pair it over here, if it was happening like this, naturally one would pair. Even if it is a high spin or a low spin, it would pair naturally. Okay, so that you need not count. So one of the pairing would happen naturally. The other ones have been happening by force, for which you have to give pairing energy, 2p. So always when you write the pairing energy of low spin complexes, compare it with the high spin complex. You will understand it better when we do the next systems. Don't worry. D7. D7. Try. So you have 1, 2, 3, 4, 5, 6, 7. So these two pairings of electrons, that has happened naturally. Everyone is singly occupied and then pairing has happened. Correct? So CFSE over here is minus 0.8 delta O, and you need not add any pairing energy. Natural. Okay. While for D7, let's see how it is. So 1, 2, 3, it cannot jump. So it will pair over here. And then seventh one would go here. So here when you compare the CFSE, so it is minus 2.4 delta O at the bottom plus 0.6 delta O at the top, which is minus 1.8 delta O total, plus how many pairing energies, what you have to write. So whenever you write the number of pairing energies, you have to compare it with the high spin complex. So in the high spin complex, already two sets are paired. You need not consider them. This one is extra. So this will come out to be one pairing energy. Compare. Already naturally paired, that would happen here as well. So you need to consider only this one, for which one pairing energy. Okay? Got it? Important, this was asked. D8. Try it out. So you have 1, 2, 3, 4, 5, 6, 7, 8. Naturally, this is what happens. CFSE you can calculate corresponding to this configuration would be minus 1.2 delta O. Okay, let's say it was paired initially. 1, 2, 3, and then 4, 5, 6 got paired over here, 7 and 8 over here. Here also, the CFSE value would be the same. No pairing energy. Why? Because here also there are 3 sets of paired electrons. Here also only 3. So that's it. D7 is the important case. Just keep it in mind. Okay, so let's do a question and then we'll wind up the session. Note down the question. For cobalt L63 minus, where L is uninegative, monodentate ligand with, see the info which is given. Crystal field splitting energy is equal to 12,000 centimeter inverse, and the pairing energy is 15,000 centimeter inverse. Question is to calculate the CFSC. Very easy question. So it is uni-negative. What would be the oxidation state? X minus 6 is equal to minus 3. X is in plus 3. Cobalt plus 3 configuration is D6. So you have to fill 6 electrons. And already it is given that is the splitting energy for octahedral complex, 6 ligands over here. So you will have T2G at the top, bottom and EG at the top. T2G at the bottom, EG at the top. Understand that the pairing energy is greater than delta O. That means the electrons won't try to pair. The pairing energy is high. So instead it will overcome the splitting energy. So you have 6 electrons, right? So 1, 2, 3, 4, 5 and 6 will be the configuration. Why? Because the pairing energy is high. So it will first overcome the splitting energy and then only pairing will happen. Correct? So what is the configuration? T2G4EG2 it is. and corresponding to which the CFSE is how much? It would be minus 0.4 delta O. You know the value of delta O? Minus 0.4 into 12,000 centimeter inverse it is. 12 into 4 is 48, followed by 3 zeros, 1 decimal, 4,800 centimeter inverse. This is the crystal field stabilization energy. Okay, this part is easy. You have to understand that if the pairing energy is high, first of all, it will try to overcome the splitting energy and then only pairing will happen. So this is what is important. Fourth one would come here. That is important. And that is because the pairing energy is high. All right. Okay, so with this, we have come to an end of the basics of crystal field stabilization energy, splitting energy, and so on. The next session, we'll have applications. So before that, we'll release an assignment. Okay, let's do an assignment and then proceed. Okay, so see you in the next.